Hi everyone. Today we're going to cover the first in a series of lectures that cover the topic of the geological theory of plate tectonics. We're going to start today with a concept known as continental drift. While some researchers proposed a similar concept, the very first person to officially, professionally propose the concept of continents moving around on the surface of the Earth was Alfred Wegener. He was a German meteorologist with a background in polar meteorology and geology. And he formally proposed that the continents moved around on the surface of the Earth so that they were compiled into a single supercontinent around 250 million years ago, and that they broke apart and moved to the positions that they currently reside in today over the period of around 250 million years. In the early 1900s, he came up with a series of lines of evidence that allowed him to propose this concept of continental drift. What happened was he lined up reasoning that showed that the continents were joined together around 250 million years ago in a landmass that he called Pangaea. It was Greek for all land. And he proposed that this landmass that we call the supercontinent, the northern portion was made up of the continents that we think of as the northern hemisphere continents. We called Laurasia, which was for Laurentia, which is the geological name for a continent that becomes North America, and Asia for the Asian continent, which is also connected to Europe. In geology, we tend to call Europe and Asia Eurasia for the name of the geologic plate that we'll talk about later in the plate tectonics lectures. The southern continents were joined together in a supercontinent, the southern part of the Pangaean supercontinent, in a place called Gondwana, and sometimes referred to as Gondwana Land. That's a name for a portion of the current subcontinent, India, and India was in the southern hemisphere at this time period and wouldn't move to the northern hemisphere until later. So the southern continents included South America, Africa, Antarctica, Australia, and India, and they would break apart to form those continents later. So we're going to step through each of Wegener's lines of evidence that allowed him to generate his hypothesis for continental drift. The first is probably the most obvious and had been proposed by individuals prior to Wegener, but he was the first one to provide evidence of it, which is that the coastline of the continents actually is a mirror image of each other. So if you look at, this is most easily seen if you look at the east coast of South America and the west coast of Africa, they tend to have the same sort of mirror image of each other as if they had been together at one point in time, and that actually is the case. If you splice the continents back together using the edge of the continent, not the coastline, but the geologic edge of the continent, then their fit is something around 95%. There's a little bit of overlapping gap, but overall the fit of the continents is surprisingly well preserved considering it's been 250 million years since they were torn apart. Wegener's second line of evidence was that if the continents had actually been joined together at one point in time, and were later separated, say, by the Atlantic Ocean, then rock types and structures on either side of that dividing ocean should be similar. We see that as evidenced in the Appalachian Mountains in the eastern side of North America that continue on into Canada. And then there's a continuation of that mountain range that's now been separated and is in the east coast of Greenland and in the British Isles and in Scandinavia. They give different names because the people who live there name their mountains differently, but they were at one point in time a giant mountain range that bisected Pangaea and was the result of previous continents colliding together to form the supercontinent. Wegener also used fossil evidence. Now these are fossils that are non-marine, so they would have no ability to transport themselves across thousands of miles of ocean basin, and he proposed that animals like Synagnathus and Lestrosaurus and Mesosaurus, which were reptiles that were either freshwater or terrestrial and had no ability to swim across an ocean, should be isolated to a single continent, but they're not. And instead we find them in South America and Africa in the case of Synagnathus, and in Africa, India, and Antarctica in the case of Lestrosaurus, and in South America and Africa also for Mesosaurus. Their biological distributions don't make any sense unless we put the continents back together, in which case they could have lived in a terrestrial environment along those connected land masses. Other individuals at the time that Wegener was proposing this hypothesis suggested there would be land bridges that were discovered, and that the animals walked across those bridges and were transported from continent to continent because they found it difficult to believe that the continents moved around. Our current investigation of the seafloor, which we'll talk about in a later lecture, disproves that, and the existence of land bridges has been shown to not be the case. Instead, the continents are moving around and have taken apart what was a perfectly reasonable biological distribution and spread them by 1,000 miles or more with ocean in between. Because Wegener actually had a background in polar meteorology, he was able to use glacial evidence as well. There are glacial deposits, so what's important to know from geology is that glaciers leave behind really distinct characteristics. The giant landmass glaciers, like continental glaciers like what we see in Antarctica and Greenland, leave scars on the rocks that show what direction they were flowing and where they were the thickest. So if you look at modern glacial evidence that's preserved from the time of around 200 to 250 million years ago, there are ice masses in South America, Africa, India, and Australia that don't make any sense. They flow from the coastline inland. And what we know today is that areas like Antarctica and Greenland that are covered by ice, the ice is thickest in the center and flows out towards the coast downslope. So if you take the southern continents of Gondwana and piece them back together in the way that Pangaea would have been located 250 million years ago, then the evidence of glaciation returns us back to a very large glacial landmass that's centered in Antarctica and flowed out towards South America and Africa and India on a giant continental glacier. That makes much more sense, and that was what Wegener proposed. Further lines of evidence that Wegener didn't use but that came to light later reside in the concept of paleomagnetism. We use the magnetic properties of minerals within the rocks to identify where they came from latitudinally. So the Earth itself is like a giant bar magnet. Its iron and nickel-rich core have a magnetic field that are generated from them. The liquid iron outer core that we'll talk about in a later discussion flows around the inner core. This generates a large magnetic field, and that magnetic field flip-flops and also induces a reorientation of magnetic minerals in sedimentary and igneous rocks. They line up with the Earth's magnetic field, and that shows that the poles themselves, while the magnetic poles wander around a little bit, don't move as much as what the continents would have shown. So the ancient magnetic characteristics of the rocks only make sense if the continents are allowed to move from place to place. What happened then 200 million years ago is the continent of Pangaea, as it was seen in the uppermost figure, breaks apart through a process of rifting that we'll discuss in another lecture, and separates into the modern continents that we see in the lowermost figure in your slide. This is called rifting and shows the continents moving from one place to another. Wegener, while he lined up great evidence for the continents actually migrating on the planet Earth, didn't have a very good explanation for the process that allows that to occur. So he said, here's good evidence for continental drift, and when somebody asked, well, how does that work? He didn't have a great answer, and some of the answers that were derived from his evidence didn't hold true. And it wasn't until we had a better understanding for the sea floor and its characteristics that we were able to develop a process by which continental drift could be allowed to occur. So we will see the evolution of the concept of continental drift turn into the theory of plate tectonics as we have more observations and a better explanation of the process that's going on.